starting with Dr. Shep Doleman, EHT's director.
Thank you, assembled guests, black hole enthusiasts. Black holes are the most mysterious objects in the universe. They're cloaked by an event horizon where their gravity prevents even light from escaping. And yet, the matter that falls onto the event horizon is superheated, so that before it passes through, it shines very, very brightly. We now believe that supermassive black holes, millions, even billions of times the mass of our sun, exist in the centers of most galaxies. And because they are so small, though, we've never seen one. There, though, they can outshine the combined starlight of all the constituent stars in those galaxies. The best idea we have of what they can look like come from simulations like this. The infalling gas that's superheated lights up a ring of light where photons orbit the black hole. And interior to that is a dark patch where the event horizon itself prevents light from escaping. The Event Horizon Telescope project is dedicated to the idea that we can make an image of this black hole, that we can set a ruler across this shadow feature, measure the photon ring, and test Einstein's theory where they might break down. It also will allow us access to a region of the universe where we can study precisely the energetics and how black holes dominate the cores of galaxies. To do this, we worked for over a decade to link telescopes around the globe to make an Earth-sized virtual dish. The aim is to, the Event Horizon Telescope achieves the highest angular resolution possible from the surface of the Earth. It's the equivalent of being able to read the date on a quarter in Los Angeles when we're standing here in Washington, D.C. In April of 2017, all the dishes in the Event Horizon Telescope swiveled, turned, and stared at a galaxy 55 million light years away. It's called Messier 87 or M87. And there's a supermassive black hole at its core. And we are delighted to be able to report to you today that we have seen what we thought was unseeable. We have seen and taken a picture of a black hole. Here it is. This is a remarkable achievement. What you're seeing here is the last photon orbit. What you are seeing is evidence of an event horizon. By laying a ruler across this black hole, we now have visual evidence for a black hole. We now know that a black hole that weighs 6.5 billion times what our sun does exists in the center of M87. And this is the strongest evidence that we have to date for the existence of black holes. And it is also consistent, the shape of this shadow, to the precision of our measurements with Einstein's predictions. The bright patch in the south that you see tells us that material moving around the black hole is moving at light speeds, which is also consistent with our simulations and predictions. And this image forges a clear link now between supermassive black holes and the engines of bright galaxies. We now know clearly that black holes drive large-scale structure in the universe from their home in these galaxies. And we now have an entirely new way of studying general relativity in black holes that we never had before. And as with all great discoveries, this is just the beginning. So imaging a black hole doesn't come easily. I can tell you that from personal experience, as can many people here in the audience. It's required long-term developments, a committed team, but it also required some very interesting cosmic coincidences. Take, for example, the maelstrom you see before you, like the hot gas swirling around the black hole. A photon has to leave from close to the event horizon, travel through the hot gas in falling to the black hole, and light rays of a millimeter wavelength, radio waves, can make that journey. Not all of them can. Then that radio wave has to propagate 60,000 years through the M87 galaxy, and then another 55 million years through intergalactic space. And then it winds up in the Earth's atmosphere, where its greatest enemy, the greatest danger, is that it will be absorbed by water vapor in our own atmosphere. So the Event Horizon Telescope uses telescopes at high dry sites so that we can see the photons that have traveled to us so far. So far, so good. We have the photons. But the M87 shadow is very, very small compared to the galaxy that surrounds it. So in order to see it, we needed to build a telescope as large as the Earth itself, given the wavelength of light we were trying to observe. And to do that, we use a technique called very long baseline interferometry, which you can see a schematic of here. Radio waves from the black hole hit radio telescopes, where they're recorded with the precision of atomic clocks that lose only 1 second every 10 million years. When you've registered these radio waves so precisely, you can then store them on hard disk drives, send them to a central facility where they can be combined precisely. It's exactly the same way that a mirror used at an optical telescope reflects light perfectly and in synchronicity to a single focus. And when we do this, we can synthesize a telescope that has the resolving power as though we had one the size of the distance between these telescopes, truly turning the Earth into a virtual telescope. All the sites that we used can be seen here. We have telescopes from Hawaii to Arizona to Mexico to Chile to the South Pole and Spain. But even this broad global network is not enough by itself to make an image. You can think of them as being silvered spots on a large global mirror. The key is that the Earth turns. During a night of observing, we are able to sweep out more baselines, more coverage of this virtual mirror to make our image. So on the left, you'll see the Earth turning. Every pair of telescopes provides us with one point on the center panel, which fills in the Earth-sized virtual lens. And on the right, you see the evolving image. The more and more data we get, the more we fill in this virtual mirror, the sharper our view of the black hole becomes until you wind up seeing what we have as the final image there. So we've taken advantage of a cosmic opportunity. It's remarkable when you think about it. Light that left near the event horizon, traveled all the way through intergalactic space. It hit our telescopes. The Earth just happens to be the right size. So we get resolving power so that we can see the black hole in M87, whose mass and distance let us observe it. And then the Earth turns to fill in our mirror so that we can make this image. It's truly remarkable. It's almost humbling in a certain way. Now, we are 4 members of a large collaboration, and it is our distinct honor to be here to represent that collaboration. We are 200 members strong, we have 60 institutes, and we are working in over 20 countries and regions. We consider ourselves really to be explorers. Through international cooperation and innovation, we've exposed part of the universe that we thought was invisible to us before. It's our responsibility now to report these findings, and we're doing that today to the National Science Foundation, to our funding agencies, international and foundations, and to all people who support pioneering research, and also to the taxpayers. Nature has conspired to let us see something that we thought was invisible. This is a long-sought goal for us, and we find it tremendous, and we hope that you will be inspired by it too. Thank you, and now let me introduce Dan Maroney, who has literally gone to the ends of the Earth to collect some of the data that we've seen here today.
Thanks, Chip. So, I should advance the slide. There we go. So the heart of our measurement is, of course, the Eht Array. It would have been an expensive, enormous undertaking to build a dedicated array just to do this experiment. So we didn't do that. Instead, we built an international partnership that allowed us to use submillimeter telescopes all over the world. In fact, we used basically all of the submillimeter telescopes in the world to make this measurement, one that none of them could have done on their own. When you take a heterogeneous collection of telescopes and build them into one giant telescope, it presents a lot of technical challenges. And so in the years leading up to our 2017 experiment, we went telescope by telescope all over the world, installing the specialized hardware we needed to do this. Most of the telescopes had detectors that we could use, but almost none of them had the atomic clocks we need, and certainly none of them had the very fast data recorders that we use. Some places we had to do even more. A good example of this is the Alma telescope in Chile. It's a 66 telescope array. It's by far our most sensitive telescope, and its sensitivity is transformational for our experiment. But in order to use it, we didn't just need the basic hardware, we also needed a special piece of hardware that could sum the light from all the telescopes before we sent it to our recorders. This alone was a many-year project using an international collaboration of people from the EHT and also from the Alma project. Another good example is the South Pole telescope. The South Pole is a special place in our array. It's so far south that it doubles the resolution of the EHT for sources it can see. But the SPT was designed to do a completely different kind of measurement. It studies the cosmic microwave background. And so its detectors are not the detectors we need. So in addition to bringing down an atomic clock and all the tens of crates of hardware that we needed, we had to build a special receiver that would detect the light the way we need it detected, special optics to relay the light to it, and install it and get it to work in the cold and sometimes harsh Antarctic environment. This was many years of work for many of us, many trips down for myself and graduate students and postdoc and other engineers in the EHT team. But at the end of it, we had a South Pole telescope that could be an EHT station. Now, getting the sites to work isn't the end of the process. We also had to test them all, because in VLBI, you really only get one shot. Everything has to be working exactly right when the script starts. So we spent years taking site by site, pairing them up, and making sure that our VLBI observations would work. The last of these observations was in January 2017. By March of 2017, we knew that that test had worked, and we were ready to go. The image that Shep showed was from April 2017. And for that campaign, we sent our team to the telescopes all over the world. Their job was to turn everything on, do very extensive testing, and then be there to do the observations. But even with all of that in place, we still had to wait for weather. And my experience with 10 years of doing these observations is that weather is usually the place where we fail. We have to have good weather in Hawaii and Spain at the same time, in Arizona and the South Pole, and that's a lot to ask. But in 2017, we were very lucky. Our first 3 days of observations were some of the best weather we've ever seen. And for a 10-day campaign, we were done in only 7, taking all the data we wanted. At the end of that, we had 5 petabytes of data recorded. It was recorded on more than 100 of these modules, and it amounts to more than half a ton of hard drives. 5 petabytes is a lot of data. It's equivalent to 5,000 years of MP3 files, or according to one study I read, the entire selfie collection over a lifetime for 40,000 people. The image you saw, though, isn't 5 petabytes in size. It's a few hundred kilobytes. So our data analysis has to collapse this 5 petabytes of data into an image that's more than 1 billion times smaller. We do that in many steps. The first of those steps is to get these modules to our correlators in Westford, Massachusetts, and Bonn, Germany. The fastest way to do that is not over the internet. It's actually to put them on planes. There's no internet that can compete with petabytes of data on the plane. Once they're there, the correlator's job is to find the exact same wavefront of light arriving from the black hole at each telescope. Once it's found small timing corrections that line up those waves, we can condense our data, we can average it, and we reduce our data volume by a factor of 1,000. Now we're at terabytes, a much more familiar unit. But we have a lot more work to do. The data still have imperfections at that point, both from the instruments themselves and from the atmosphere above the telescopes. And so we do something called fringe fitting. We actually do this in the cloud with cloud computing, which lets us do it in days instead of weeks. We calibrate the data so that we know exactly how bright our sources are. And I'm speaking of this as though it's just computer work, but this was actually a very significant project for a subset of our team, primarily junior people, postdocs and graduate students. And they deserve an enormous amount of credit for their diligence and dedication, because without it, we couldn't have made an image. Once we're done with that, we can finally go to the imaging stage. Now, imaging with an interferometer isn't as simple as downloading a picture from your camera. Fortunately, though, the math that we use for it has been around for more than 200 years. The principle is well understood. The methods, though, as with everything with this project, are a little tricky for our data. And so in order to get to the image, there's been years of image algorithm development within our team that's been essential to our results. At this point in history, we have many different image algorithms to choose from. They have different strengths and weaknesses. It just depends on the character of the data. And so the way we approached the imaging stage is we set up 4 teams all over the world. They were collaborating. Each team is representing many parts of the world. And we told them, don't talk to each other or anyone else. Choose whichever imaging algorithms you think are best and make images of these data. And then in the summer of 2018, we brought everyone back together at a very exciting meeting, the EHT Imaging Workshop in Cambridge, Massachusetts. If you couldn't be there, you certainly called in from the internet because you wanted to see the presentation. And in a very exciting presentation, we revealed to the other teams and to ourselves what we'd found. And what we saw in those images were 4 very similar pictures, looking almost exactly like the one you see today. An emissive ring surrounding the shadow of a black hole. It was a wonderful day of science, and I'm glad that after a few more months of very careful checking and paper writing, that we're finally able to share it with you today. And now I'd like to hand off to my colleague Avery Broderick to talk about the interpretation.
Thank you, Dan.
Congratulations.
Thank you. Thank you, Dan. It is an enormous pleasure to be with you this morning to share in this extraordinary moment. As Shep said, we have now seen the unseeable. Now, what does it all mean? Every photon in these first EHT images began its journey in a churning maelstrom embedded in the most extreme environment in the known universe, the vicinity of a black hole. In M87, the crucible in which these photons were born was powered by the black hole in 2 distinct but related ways. First, via an accretion flow. A violent disk of orbiting gas driven inextricably toward the event horizon. By the time the material is making its final plunge, it is crashing into itself at nearly light speed, transforming the gas into 100 billion degree plasma. Second, through astrophysical jets. Narrow beams of outflowing material speeding away from the black hole at nearly the speed of light. These jets are powered by black hole spin. Rotating black holes drag everything, gas, magnetic fields, and photons about themselves, driving these paradoxical structures whose cosmic importance will be discussed by my colleague Sarah Markov. In M87, one of these jets is pointed very nearly toward us. The EHT images are influenced both by these bright emitting regions, the rotating accretion disk and outflowing jets, and by gravity itself. In general relativity, radio waves fall just as apples do. Typically, this effect is exceedingly small, but black holes are gravity run amok. The radio waves we see in these first images orbited the black hole before beginning their 55 million year journey toward us. This results in the dark shadow or silhouette cast by the black hole's event horizon upon the emission from the accretion flow in the jet. Importantly, the size and shape of the shadow is determined by gravity alone. General relativity makes a clear prediction for both of these features. To within 10%, the shadow should be circular, with a diameter determined solely by mass, multiplied only by fundamental constants. However, as with all voyages of discovery, when we began this expedition of the mind, we did not know what we would find. Were Einstein wrong, or the object at the heart of M87 not a black hole, its silhouette could have been very different, misshapen or missized like those seen here, or even simply missing. Changing gravity changes how light bends, and thereby changes the shape of the shadow. In April 2017, this was the dog that did not bark. The shadow exists, is nearly circular, and the inferred mass matches estimates due to the dynamics of stars 100,000 times farther away. Today, general relativity has passed another crucial test, this one spanning from horizons to the stars. This shadow is surrounded by a bright ring of enhanced emission. Oh, we'll skip this. Enhanced emission due to those photons that just escaped the black hole's clutches. The properties of this ring-like feature result from the astrophysical dramas that unfold on gravity's stage. To understand these dramas, over the past 3 years, the EHT collaboration has undertaken an unprecedented simulation effort at research institutions across the globe. This has generated the largest collection of simulations ever assembled of the accretion flow and jet launching region in M87. The southern brightness excess arises directly from near light speed rotational motions near the black hole. Regions that move toward us at nearly the speed of light are bright. Those that are moving more slowly or away are dim. From these, we have inferred the sense of rotation of the black hole. In M87, the black hole spins clockwise. Moreover, the excellent quantitative agreement between the EHT images and generic theoretical expectations of a bright crescent-like feature with a dark interior provides significant confidence in our interpretation. The object at the heart of M87, the object that powers M87's jets, is a black hole like those described by general relativity. Importantly, in combination with infrared and optical flux measurements, we can now rule out a dim but otherwise visible surface. That is, this does indeed appear to have the defining feature of a black hole, the event horizon, that point of no return. Today, several complementary windows have opened upon black holes. Science fiction has become science fact. Together, two of these windows, the EHT and LIGO, which reported the first detection of gravitational waves a short 3 years ago, have verified another key prediction of Einstein's theory of gravity. Despite varying across a factor of billion in mass, known black holes are all consistent with a single description. Black holes big and small are analogous in important ways. What we learn from one necessarily applies to the other. At this point, I would now like to hand the story off to Sarah Markoff, who will describe the broader astrophysical implications of these first EHT images. Thank you.
Thank you, Avery. So black holes may be the most exotic consequence of general relativity, but these bizarre sinkholes in the actual fabric of space-time turn out to have a lot of consequences of their own, which I'm going to talk about today. That's because black holes are major disruptors of the cosmic order on the largest scales in the universe. And they're actually helping mold the shape of galaxies and clusters of galaxies. Well, we've now confirmed, as Avery was saying, that general relativity itself does not change when we look at different black hole masses. It turns out that the impact of a black hole will actually change a lot. And so if we want to understand the role of black holes in the universe, then we need to have accurate determinations of the black hole masses. And this has been a problem up until now. So actually, our mass determination by just directly looking at the shadow has helped resolve a longstanding controversy in measuring the mass of M87. There's been two independent methods, both basically looking at the motions of either gas or stars, but they ended up giving different answers. Our determination of 6.5 billion solar masses lands right on top of the heavier mass determination from stellar motions. And so this actually will also help resolve a discrepancy that can lead to better mass determinations for other more distant black holes where we can't actually see the shadow. So getting to the impact of this is important because M87's huge black hole mass makes it really a monster, even by supermassive black hole standards. So you're basically looking at a supermassive black hole that's almost the size of our entire solar system. And in fact, that's part of the reason that we can see it, even though it's so far away. But if we now zoom back out to the more cosmic perspective of the host galaxy of this black hole, the galaxy is made of billions of solar systems, and so on those scales, the black hole itself is minimally small. It's about 100 million times smaller than the galaxy. And if it were a dormant black hole, like the supermassive black hole in the center of our own galaxy, Sagittarius A star, then the galaxy would really have no way of knowing it's there and would basically be just like a pebble in a shoe. But when a black hole is what we call activated by gravitationally capturing material, it starts to convert that fuel into other forms of energy with an efficiency that can be almost 100 times better than nuclear fusion that powers the stars like our sun. And so when that happens in these active phases, black holes temporarily become the most powerful engines in the universe. And they go very quickly from being a pebble in the shoe to a thorn in the side of the galaxy, literally. And the thorns in this case being the jets that Avery was mentioning. In the most extreme cases, these jets can actually penetrate through the entire galaxy and well beyond. But the power that's coming out, we can't see with our own eyes. So if we want to understand them, we have to look in other wavelengths. So we look with telescopes across the electromagnetic spectrum. So I'm going to give you an example of this. This is another very active black hole system, and it's a combined image. So you see in white from NASA's Hubble telescope, the elliptical galaxy Hercules A in the center, and then overlaid in blue is the radio waves from the National Science Foundation's Very Large Array. And these radio waves are basically tracing magnetic fields in space. So this tells us that these jets are just enormous fountains of magnetized material that are being sprayed out from the black hole, not the black hole itself, but near the black hole, nearly at the speed of light. And these particular jets are 100 million times bigger than the black hole that launches them. Now, if we add another layer, we're going to look in the X-rays now from NASA's Chandra telescope, and X-rays are probing extremely hot gas, like billions of degrees. So we're seeing the entire system is embedded in a halo of hot gas, and we can use this information to calculate how much energy the jets had to have to bore through all this material. And what we find is that the jets are carrying the equivalent of 10 billion supernova in energy deposited over one of these active cycles. So this is, these kinds of interactions are basically very important because this tiny black hole on these scales is somehow launching these structures and also managing to heat the gas to prevent stars from forming. And since galaxies grow by forming more stars, this has the effect of truncating galaxy growth. And we think it's through these types of interactions that black holes help shape the largest structures, galaxies and clusters of galaxies, and make them look the way they do today. Now, M87 is in a much more modest active state, but as you can see, this is also from Hubble. It's still managing to launch pretty magnificent jets, and these jets are emitting across the electromagnetic spectrum as well. So we need this information to be able to fully understand the system. But if we zoom way out now to the cluster of galaxy scales, this is another combined image where you see red in radio and blue in X-ray. You see just a mess of structures, and we think this is telling us about M87's black holes' past interactions really affecting the cluster scales on time scales of hundreds or tens of hundreds of millions of years. So until now, well, we always thought that black holes were behind these large structures, driving these engines, but we never knew. And now with EHT, we have direct evidence of the root of these problems, and we can look at this, and we can now start to make, to understand, oh, there we go, combining strong gravity, magnetic fields, and looking at atomic level processes to understand how these processes interplay and conspire to make these enormous structures that are basically affecting the largest scales of the universe. And so to capture all of this information, we need to combine our observations with those across the multi-wavelength spectrum. And so, as you heard from Dan, there's a lot of complexity in these observations, and we added to that by doing a complicated Sudoku of coordination with many facilities across the globe and also in space. And this is similar to the campaign that was run with LIGO for gravitational waves. It's very important to combine signals, both from photons and particles. And so by doing this, we expect that EHT is going to play an active role in this new era of international multi-messenger astronomy. So anyway, looking to the future, the same observations that we took in 2017 that for M87 also included this dormant black hole in our galactic center, Sagittarius A star. And by looking at two black holes at opposite extremes of this activity range, especially combining this with multi-wavelength information, we can better understand the ebb and flow of influence of black holes in the long course of our history in the universe. Anyway, so thank you very much. I'm going to hand this back over to Shep, who's going to say a few words.
Thank you, everyone. I just want to point out that when we first started the Event Horizon Telescope project, the group was small, and I think it had to be small and nimble to carry out precursor experiments and develop the first kinds of techniques and instrumentation that enabled us to move the field forward. But over the past decade, the greatest accomplishment has been the building of a team. And as I said before, we're now 200 people strong, many institutes, over 20 countries and regions. And if you want to reduce petabytes of data, if you want to develop new imaging algorithms, if you want to image a black hole, then you need a large team. And it has included many early career scientists, senior scientists, and many of them are here with us today. So I'd like to ask everyone who's associated with the Event Horizon Telescope to please stand up so that everybody in the media can see who has done this work. It's a true pleasure and privilege to work with this crew. And I urge all the media to please go seek them out to learn how the sausage was actually made, how the black holes were actually imaged. I also want to say something in particular about funding and support. This has been a high risk but high payoff endeavor. Sometimes you have to kiss a lot of frogs before you get the prints, before you get the black hole image. And you need supporters, you need funders who will stand by you for long periods of time, who take the long view, who understand that basic science never goes out of style, and who also understand that basic science, you never know when it's going to pay off, but ultimately it usually does, and that you have to play the long game. And we had wonderful partners with the National Science Foundation, with our international funding agencies and foundations, and our hat is off to them for sticking by us for so long. And we look forward to greater things with the EHT as we build out the capability and we continue to sharpen our focus on black holes. Thank you.
Thank you all very much. One note before we take questions. Several of our panelists and many of their EHT collaborators will appear this week in a documentary which has followed the efforts of the EHT for the past 2 years. The film will show viewers just how Shep Doleman and his team reached the groundbreaking moment. The documentary is called Black Hole Hunters, and it will premiere this Friday, April 12th at 9 p.m. Eastern on Smithsonian Channel. We will now take questions from the audience until 10 a.m. Please raise your hand, wait for a microphone, and identify yourself and who you are with before asking your question.